Welcome to the Solving Logs video. Sorry about my voice. I'm getting over a little bit of a cold. So, what we looked at in class the other day was the one-to-one property. We have if b to the x equals b to the y, then x equals y. This property we can use when we have two things in exponential form and we have the bases that we can make the same. Like if we had 10 and 100, we could make that 10 and 10 squared so that we have the same base. Then we can set the exponents equal. Another strategy is exponentiate. In that video some of us watched, the gentleman said, "B it up," which really is just exponentiating with b as the base, but we'll look at an example of that. Taking a log of both sides, and that's using that property so that the inverse operations end up giving us isolating that x. Also, this property is very useful. We have a log base b of m and a log base b of n. Well, if they have the same base, then the m and n are going to be equal. Another strategy is just change forms, which you guys are really good at. Taking that from exponential form to logarithmic form. And then using the power properties. So if we're adding two logs, we can condense it and make it a multiplication. So this really is the expand condense. Condense. Okay, oftentimes we're not expanding and we are condensing, but I can think of a couple situations where expanding might be helpful and we can simplify. Alright, so let's look at an example problem for each of those. Here we started off with 9 to the 2x and 3 to the x minus 9, x minus 6, 3 to the x minus 6 and 9 to the 2x. But then we changed that 9, we replaced it with 3 squared. Now we didn't do something to just one side of the equation, we just replaced something with something that's equal to it. So we just changed the way it looks. Like I always say, $1 is the same as 4 quarters. We're just replacing it with an equal amount. Once we have the same base, we can set the exponents equal and solve for x. With exponentiating, we have log base 3. If we want to get rid of that log base 3, we can exponentiate with a base of 3. And we could also call it 3 it up. So if we 3 it up, this is now the base, and that's the exponent. This is also the base, and that's the exponent. A base, so that using this property, the base with log base b, this and this, because they're the same base, they are inverse operations, and they almost like cancel each other out. I don't want to say cancel, they undo each other. So we end up with just 2x minus 1 equals 3 cubed, which is 27. And then this is just algebra 1 kind of problem. 2x minus 1 equals 27. Add 1 to both sides, and we can get x equals 14. Alright, so we want to double check, make sure we plug that 14 in. If this argument is negative, then it's going to be an undefined answer. So we need to check and make sure that this argument is not negative. If I plug 14 back in here, I get 28 minus 1 is 27, which is fine. Alright, the next one, take a log of both sides. So this one, again, these two you could ignore. If there are too many strategies for you, these two could both be replaced with just change the form. So really what we did here, when we exponentiated, we end up changing the form. We could also go 3 to the 3rd power equals that. So just changing the form would get me straight to here. 3 to the 3rd power equals that. Same thing here. I could just change the form and go, oh, log base 2 of 15 is x. So you could get immediately to this step if you like. So taking a log of both sides, again, using that property that the base, log base 2 and the base of 2 are inverse operations. Alright. The next one, one-to-one property. Oh, this one's great. I love this one. it's so simple because you're like, oh, well, if it's balanced and there's a natural log there and a natural log there, well, those arguments must be equal. So 2x must equal 4. Oh my goodness, this complex looking problem just turned into a very simple problem. 4 divided by 2 is 2. Double check, make sure this isn't negative. We're good to go. All right, so if I plug that 2 back in, natural log of 4 is equal to the natural log of 4, so we're good. Again, these were the two examples we looked at earlier. You can change the form from exponential to logarithmic, and that can oftentimes be helpful. And the last one is this. Oops. Using properties of using log properties. Like when you add, you end up really multiplying. So here we have 2 logs we're adding. So we can condense that and make it the natural log of x times x plus 3. So we multiply those two together and get x squared plus 3x. Now, in this situation, now we can do two things. We can e it up, or we can exponentiate. Oh, I'm sorry, e it up is exponentiating. We can e it up or change it to exponential form. So log base e, we could say, e to the first power equals that. E to the first power equals x squared plus 3x. And then we'd want to solve this using a quadratic method. And in this case, I have no idea how to factor that because I'm not sure what times what gives me e that adds to 3. So I would want to use the quadratic formula and decide a is 1, b is 3, and c is negative e. This is like a challenge problem. So, all right, let's go on. So then in class we went through and we said, okay, well, what strategy would you use? So here's a couple examples. This one you need to use change of base formula with log of 11 divided by log of 3. Now, I have it solved one way, but it doesn't mean you had to solve it the exact same way. Here you get x equals 2. Now, in this case, a lot of students are like, well, wait a second, you said can't have a negative number sometimes, so we have to check. Well, if I plug this back in, you're allowed to have a negative in the exponent, you're just not allowed to have negative in the argument. All right. So those are a couple examples. Hopefully that was helpful if you needed a review or if you missed class.